So Newton's third law of motion talks about forces acting in pairs, and action and reaction force. A lot of times people say for every action there's a reaction. And that's generally true, and that's more or less what the third law is talking about, but it's an oversimplification. So the third law is described right here. Whenever one object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. So when you say that just there's, for every force there's, an equal and opposite force, or for every action there's a reaction, what we're missing is that in this case there has to be two different objects that we're talking about. You can't just have one object and two forces applying Newton's third law. That doesn't work. So that's why we're talking about forces acting in pairs, an action and a reaction force, as well as two objects. So I've got some examples here. These are all just examples to help understand what's going on. So with a chair, right, this is kind of the whole Fat Kalman thing. Your weight pushes down on the chair pushes back up with an equal but opposite force that balances your weight. If it didn't do that, right, this is the Fat Kalman example, the chair breaks, I fall to the floor. So now the floor would have to support my weight. It would apply an equal and opposite upward force to my downward force due to weight. And it stops me. Right? So at a certain point, whether or not it's the chair or the floor or the ground, something will provide that equal and opposite force that will stop my motion. So to get a little bit more complicated, swimming. When you're swimming in the water, your hand pushes against the water, and the water actually pushes back against the swimmer's hand, propelling him or her forward. So what we need to think about this is a chain of reactions, right? So water is not just one mass. It's actually millions and millions and millions of water molecules. So when your hand moves forward and hits, this is going to be a weird, if, so, you've got a bird hand. Okay, so there's your hand, and here's a million water molecules. Your hand hits all of these water molecules. They're going to move this way. They're going to bounce off of other molecules. They're going to bounce back towards your hand. These water molecules hit the side of the pool. They bounce back in this direction. So as they bounce back, and this is all happening simultaneously, instantaneously, it hits against your hand, and that's what propels you forward. So the forces do not act on the same object, but those objects apply forces to other objects. Meaning my hand applies a force, it pushes against these water molecules. Those water molecules hit against each other, which then hit against my hand and moves me forward. So, an example with a rabbit, right? And this doesn't have to be a rabbit, it can be you. The rabbit pushes down on the earth, and the earth pushes back up against the rabbit. And the rabbit we see jumping forward. With the space shuttle, right? We've often talked about rocket science. So here's our rocket. There's the person inside the rocket. Those flames come out of the bottom. That is a whole bunch of particles shooting out down towards the Earth. Those particles hit against the Earth, they hit against each other, and they provide a force back up against the rocket, and the rocket accelerates upwards. So in all of these cases here, whether we're talking about the human body and water, or whether we're talking about the rocket and the Earth, we're talking about objects with different masses. Right? The rocket, while it's very, very heavy, is not even close to as heavy as the Earth. If the rocket weighs 100,000 kilograms, the Earth weighs trillions of kilograms. So 100,000 kilograms is still like a small pebble compared to the Earth. So what this is explaining here is why we only see one object move. Whether it's the rocket or you pushing against the Earth to jump, you don't really see the Earth move. And that's because your mass is way smaller than the mass of the Earth. So let's do some math here. We're basing it off of this. So a cannon and cannonball example is the same thing as the Earth and human example. So if the human, we're going to make this very easy, weighs 100 kilograms, and the Earth, let's say, weighs 1,000 kilograms, right? We know that's not true. It weighs way more than that. But this is to make our math easy. So the force of human, right, F of h. So let's say that human, 100 kilogram human, applies a force of 10,000 newtons, and we're going to find acceleration. Acceleration would equal 10,000 divided by 100, cross out 2 zeros, and, excuse me, that rate of acceleration would be 100 meters per second squared. That's for the force of the human. Now the force of the Earth, that 1,000 kilogram object is going to apply a force, or have a force applied to it, of 10,000 newtons. Divide it by 1,000 and 1,000 times a, and we would see that the Earth would accelerate, theoretically, at 10 meters per second squared. Now, really, because this number would have like 9 more zeros followed after it, this number wouldn't be 10, but would have a decimal place about 8 numbers in that direction, right? So, or 8 digits in that direction. So what we see here is that the human who pushed on the Earth accelerates at 100 meters per second, and this fake Earth that has a tiny mass compared to the real Earth accelerates at 10 meters per second. So the Earth does accelerate a little bit. When we're talking about me pushing against the Earth as I try to jump, the Earth moves a fraction of a millionth of a millimeter, right? It moves a tiny little bit that is so small we can't even measure it. Whereas I might jump up a foot, 2 feet, 3 feet up into the air because my mass is way smaller. This same concept applies up here to the cannon and cannonball. If you've ever seen a cannon fire, right, in a movie or rather in real life or something, does the cannon move when it fires the cannonball? Yeah, it slides back 3, 4, 5, 6 feet, but the cannonball shoots forward hundreds of feet. And that's because of the difference in mass, because of the difference of what we were talking about with these equations. Because there's equal and opposite forces, in this case 10,000 newtons, but we're talking about masses that are different, the accelerations are therefore going to be different. So this law, Newton's third law, is really just taking his first and second law, the idea of inertia and the idea of F equals m times a, and applying it to situations where something occurs where one object pushes on another object. So the explosion within the cannon, right, you ignite that cannon, there's an explosion, that pushes that on the cannon, which has a heavy mass, so it doesn't move very much, and that force then rebounds and pushes off the cannonball, which has a smaller mass, and therefore it goes flying. So we see the cannonball accelerate a lot more than the cannon would. Just like when you're jumping, we see only the human accelerate, though the Earth does accelerate a fraction of a billionth of a centimeter, right? So basically 0. There's a couple other examples with a baseball bat and a ball with gravity, but what we have to remember is that there are always 2 objects, right? So if we were going to draw this out, we're going to have object 1 with, some mass, 10 kilograms, and it pushes down with 100 newtons of force onto object 2, which has 1,000 kilograms, which is also going to push back with 100 newtons of force. So, are we going to see, which one of these 2 objects are we going to see move? A 1,000 kilogram object with a 100 newton push? Sure, it'll move a little. Right, that's just following the math of m, that should be 2 t's, of F equals m times a. But this 10 kilogram object pushed by 100 newtons, that's really going to accelerate. Moves, accelerates a lot because of the difference in masses. So just like when you're using a baseball bat to hit the baseball, essentially that baseball bat is an extension of your mass. So you as a 150-pound person against the ball, which weighs maybe 1 or 2 pounds, that ball is going to be the thing that accelerates much more than you do, right? Same thing with the Earth, same thing with the rocket, same thing with you swimming in the ocean, right? The ocean has a much bigger mass than you. So you might see the water move a little bit as you paddle, but you are going to be the object that is really propelled forward. You're not going to paddle and all of a sudden all of the ocean is out of the ocean and up on land in some big tsunami, right? That's not going to happen. So this is the third law. A little bit more confusing as it's the combination of the previous two laws applied in some scenarios here. But remember this piece here, right? We've got two objects with forces interacting there.